Math 1314, Tyler Junior College, Section 4.1, Exponential Functions. Definition of an exponential function. Up until now, we've seen quite a variety of categories of functions, if you will. We've seen linear functions, functions that look like f of x equals mx plus b. And we know everything about them. We know slopes and intercepts. We can graph them. We can interpret the slope. There's all kinds of things we can do with them. We've discussed quadratic functions, functions of the form ax squared plus bx plus c. And we've analyzed those quite a bit. We know their shape, their parabolas. We can use this leading coefficient to determine if the parabola opens up or opens down. We can even use all of the constants in the function to determine things such as x-intercepts, y-intercepts, the vertex, and all of that information can be used to graph. And we can also apply quadratic functions, usually when trying to find maximum or minimum values for certain functions. We've also talked about polynomial functions in general. A function that begins with some unknown power of x, or rather it can be any power of x, it's usually known, and then some coefficient in front of it, which we generically call an. And then we just worked all the way down until we got to a quadratic term, a linear term, and a constant term. So basically we blew the lid off of the degree, and when we study these, we look for things like in behavior, we look for x-intercepts, and look for the behavior at the x-intercepts, whether the graph crosses or touches the x-axis. We found the y-intercepts, and we really analyzed those quite a bit. And most recently, we've analyzed rational functions, such as some polynomial like 3x plus 1 over some other polynomial like x squared minus 4. And when we analyzed these, we had to address the domain issues because there's a denominator, there's a possibility it could be 0, and we had to avoid that. We located some of the standard things like x-intercepts and y-intercepts, but with rational functions, we also had the introduction of horizontal and vertical asymptotes. Just for kicks, can you look at this and spot both the vertical and horizontal asymptotes? I know this was the previous, actually it was 2 sections ago, but if the denominator were 0, that's a potential vertical asymptote. That would be 0 at 2 and negative 2. In fact, they would be vertical asymptotes because neither of those simultaneously make the numerator equal to 0. And for the horizontal asymptote, we would just compare the degrees of the numerator and the denominator. Since the degree of the denominator is greater, the horizontal asymptote on this would be 0. But I digress. My point is we've analyzed quite a few functions. The next category of functions we're going to look at are called exponential functions. What makes a function exponential? An exponential function is a function whose variable is in the exponent. That makes sense. But nowhere else. Now, if there's something living in an exponent, then there has to be a base that it's on. For example, if I said 3 to the second power, 2 clearly is the exponent, but this 3 would be called the base. And since an exponential function can only have a variable in the exponent, then we can conclude that the base is going to be a number. Now, the number for the base does have some restrictions. The base can be any real number as long as it's positive, so greater than 0, and not equal to 1. The reason we exclude 1 as a possible base is if you have a function like f of x equals 1 to the x power, this isn't really an exponential function, it's a constant function, because 1 raised to any power is 1, so it's kind of redundant to even say to the x power. So we eliminate the possibility that the base is equal to 1. There's another reason the base isn't equal to 1. When we get to the next section, 4.2, you'll see why. Alright, so in this video, all I really want to do is give you some examples of exponential functions and examples of some non-exponential functions. Exponential functions can be very small. For example, you can have something like f of x equals some number, we'll say 2, raised to the x power. Not a whole lot to look at there. We could also say something like g of x is equal to 0.75 to the x power. Remember, the base can be any positive number as long as it's not 1. But the definition, or at least my definition of exponential function, allows for more than just this. And I should really say my definition of exponential function. If you look in the textbook, in the beginning of section 4.1, the author will say an exponential function is a function of this form. Some base raised to some x power, or the base has the same restrictions that I've listed here. The problem with this is these aren't the only types of exponential functions as you're about to see. What makes this exponential is the variable in the exponent, but it really has no restrictions on what else the function can have. For example, we could say h of x equals 5 times 2 to the x plus 1 power, and then minus 2 after that. That would be an exponential function. The variable's in the exponent, nowhere else. But if you notice, I've dressed it up quite a bit. In fact, you can think of h of x as a transformed version of f of x, where we took a base function, a parent function, if you will, and we did some things to it. We added 1 to the x. We subtracted 2 at the end. We multiplied the front by 5. And if you're starting to think, wait a minute, would these numbers do the same things to the graph of this that they've done in the past? Specifically, would this plus 1 move the graph of this to the left 1? Would this minus 2 move the graph of this down 2? And would this 5 invoke a vertical stretch by a factor of 5? Yeah, it would. But that's about 3 or 4 videos down the road, so we'll get there. Also, we'll call this one, we can't call it I of x. I is reserved for the square root of -1. So we'll call it j of x. Your exponent can do more than just have an x. For example, you could have something like 3 to the x squared plus 2x plus 1. And that technically would be categorized as an exponential function because the variable only appears in the exponent and nowhere else. So what are some examples of non-exponential functions? Well, we've already seen a lot of them. In fact, everything that I listed a moment ago is a non-exponential function. But the confusion some people have is when they see the word exponential, they think the function has to have an exponent, which is true. But we've seen functions with exponents like f of x equals x squared before, and that's not an exponential function. Yes, it has an exponent, but what makes a function exponential is the location of the variable in the exponent. In this case, the variable is not in the exponent. Square root functions. That's not an exponential function. Variable's not in the exponent. You might say there's not even an exponent, but in the next video, you're going to see there really kind of is. Here's a little foreshadowing. The square root of x is equal to x to the 1/2 power, but don't worry about that yet. We'll talk about that in detail in the next video. Or something like this. The quantity x plus 1 times 2 to the x power. And you might be thinking, wait a minute, there's a variable in the exponent, and you would be correct, except it's not the only place it is. To be an exponential function, your variable has to be in the exponent and nowhere else. This variable is also on the ground level as a coefficient in front of this 2 to the x power. So we're going to be dealing with some exponential functions. We're going to be looking at their graphs. We're going to be looking at translating the graphs like we've done in the past. We're going to look at something called the natural base. I'll say this later, but your calculator needs to have this on it somewhere. And if you can't find it, then you might want to look above this button. And if your calculator doesn't have an LN button, you need one that does. And then we'll look at a few applications of exponential functions.